In this video, we'll continue to explore this fascinating idea that when I sit down to eat steak, or tofu for that matter, there are chemicals in my digestive tract that actually disassemble the protein in the steak down to the individual amino acid. I can't safely have steak floating around in my bloodstream. It would cause coagulation. It would be recognized as a foreign antigen. I could, if I survived having a chunk of steak in my bloodstream, I could develop a lifelong allergy to beef protein, a fate worse than death. So let's see how this works. How do I disassemble food down to that very level? Well, in order to really understand that, we have to look a bit more closely at the structure of the GI tract. GI tract really stands for gastrointestinal tract. But most of the time when people say that, they mean the entire digestive tract, from the mouth to the anus. Here's the first truly mind-blowing thing you need to know about your digestive system. What you think of as the inside of your intestine is actually the outside of your body. Let me say it a different way. From your mouth to your anus, this entire structure, with the exception of the liver, this is all actually an external surface of the body. Your digestive tract doesn't really go into your bloodstream, not directly. There's a barrier. The epithelium separates the partially digested food from your bloodstream. The food that's in your stomach, and I'm using air quotes, in your stomach, is actually just surrounded by your stomach. It's not yet inside of your body. If you ate something bad, you could just barf it back up. And although that food would have appeared to have gone into my body, it's actually just surrounded by my body. And when my GI tract recognized that it was poisonous or contaminated with bacteria or whatever, it said, hey, I got to get this out of my body before the toxins penetrate the membrane and get into the bloodstream. So it's really mind-blowing. But if you could take a tiny camera, an endoscope, or one of these new pill forms, they put a little camera in a pill and the patient swallows it, look at the tract that it would follow. If it's in the mouth and they spit it back out, was it ever really inside their body? Well, no. The mouth is obviously an external surface of the body because I can see it. When I'm brushing and flossing, I open up my mouth, I can see all of that stuff in the mouth and the throat. So that's really just an infolding, an inward folding of what embryologically was external tissue. Logically, follow that down then. Is the esophagus the inside or the outside of your body? Well, it's actually the outside, because if I choke, I can just spit that particle right back out. Okay, so what about the stomach? It is an external surface of the body. It is just an infolding of the outside that happens to form a sac-like structure. And because we don't see it, and because it is within our abdominal cavity, logically we think, oh, that is on the inside. But that food is actually still on the outside. Okay, so right now you may be thinking that I'm just playing with language and that I'm just trying to be clever. But think about it. Histologically and immunologically, it is designed, the GI tract that is designed to keep things from getting inside my body until they have been safely digested. Here's what I mean. If I eat a peanut, I cannot have peanut in my bloodstream, or I will have a very severe allergic reaction. And so my body has designed a way to chemically break down that peanut with acid and enzymes down to the level of the individual amino acids, which can then safely enter the body. So look at the histological slice here. The peanut right here is still outside the body. It is being broken down and chemically digested. And only at this point where the amino acids are absorbed through a cellular membrane. Only then does it really enter the body. So if you had an endoscope or one of those little cameras, as I was saying, you could swallow it, and you could have that camera, at least theoretically, go all the way through and out the other end without actually passing through a membrane, without damaging anything. Again, theoretically, they don't actually do that. You can go down about this far from the top down, or you can go from the bottom up, a lower endoscopy where they can go in the rest of the way. The point, hopefully I've just sort of pounded this into the ground, but you can't safely have undigested proteins in your bloodstream. And so you also can't wait around for food to rot inside of your stomach. You have a fascinating digestive tract that will move things along, and through the use of enzymes, dramatically speed up the rate by which that food is digested and then absorbed. Here, it enters the body, flowing either into the lymphatics or the bloodstream. These yellow nerves are controlling contractions of these muscles to accomplish that peristalsis, or the mass movements, or that sort of sloshing back and forth. The whole thing is wrapped in connective tissue, like every organ, the capsule of the pericardium, the pleura, the muscular fascia. In the GI tract, we call this serosa, and it literally is the sausage casing of the GI tract. What's a brat without the sausage casing? I don't know, a meatball, ground pork. What holds it together is the sausage casing. This is a bit gross, but true. The serosa of the GI tract is what traditional sausage makers use. They just flip this inside out, strip the serosa out, dry it, and then stuff it full of the ground meat. So, man, that's really gross, but true, and it will help you to remember the important function of the serosa in your own body. Like the sausage casing, it holds the GI tract together. You'll notice that the muscular layer is divided into longitudinal fibers, which are on the outside, and circular fibers, which are on that inner layer. And it's the combination of those two types of muscle fiber contraction that accomplishes that coordinated movement of peristalsis. Oh, let me back up one slide here. The submucosa. So this is the mucosa, the mucous membrane, technically the external surface of the body. Deep to that, from the lumen, we're actually going into the body here. Although your brain might logically think this is deep and we're moving out superficially. If you think of this as the starting point, because the nutrients are going to be going into the body from the outside in, then we could really say that the epithelium is the superficial layer, and that deep to it is the submucosa, and then the muscularis, and then the serosa. Now, a surgeon or a surgical technician would obviously view it from a different perspective. If they need to get in, they would be coming from an incision or an opening in the abdominal wall, and then this would be the superficial layer. Muscle is deep, then submucosa, and then mucosa. Either way, you got to know the layers and to be able to put them in order. The submucosa is where the lymphatics are. Lots of blood vessels, so the nutrients that are digested and then absorbed flow into the body, usually to the liver first, or into the lymphatics, as we're going to find out the fats work. Okay, now we need to start to explore these ideas of how we regulate the digestive system. The coordination of movements and the release of secretions is really accomplished by two broad mechanisms. Either the nervous system is zapping the muscles or glands to make them do something, or chemicals like hormones and local hormones called paracrine secretions. It's not an endocrine secretion if it doesn't go into the bloodstream. Paracrine chemicals just float through the extracellular fluid so that one cell can stimulate cells just around it. So sometimes we call these local hormones. Histamine is one example. Gastrin and secretin are true endocrine hormones because they're released into the bloodstream. And then it is the circulatory system that circulates the hormones and helps them to find their target cells. So chemicals regulate the digestive system, and the autonomic and enteric nervous systems regulate the GI tract. Here we see a sagittal section. I think what I want you to appreciate is that just like everything else, the gut is surrounded by a double layer of connective tissue. The pericardium is a double layer, the pleura is a double layer, the peritoneum is to the gut what the pleura is to the lungs and what the pericardium is to the heart. So this is becoming very familiar language now. The visceral peritoneum must be attached to the organs, and the parietal peritoneum is attached to the abdominal wall, so the inside of your six-pack, and right along the spine and those paraspinal muscles. That's the parietal peritoneum. Notice that a few of our organs have evolved outside of that, sort of as an added layer of protection. Our pancreas is retroperitoneal, and our kidneys are retroperitoneal. And then just a small part of our small intestine is also retroperitoneal on the outside. For protection, I don't know if I'm right in this theory, but the pancreas in particular is full of digestive enzymes. And if there were a fracture or some sort of rupture, a pancreatitis that allowed these cysts to break open, theoretically we could begin to digest our own tissue. So I'm not positive, but I suspect that's why natural selection sculpted the kidneys full of wastes and the pancreas full of nasty enzymes to be outside of the peritoneum. When we think about food or see it, sometimes just have someone describe food to us, it triggers an involuntary release of saliva. Let's see if I can make you salivate. Listen to this. Imagine that you bite into a raw and juicy lemon. Isn't that crazy? Just thinking about it oftentimes triggers one to salivate. And that's because you've had such an experience that your mind knows, oh, that's going to be so sour. I got to try to wash that stuff out. And so I'm making myself salivate just by describing this to you. I am my own Pavlovian dog. The parotid glands are right up here near to the earlobes, one on each side, and they empty into the side of the mouth. The submandibular glands are just below the body and angle of the mandible, and they empty into the bottom part of the mouth. So when you really salivate, you sort of feel this sensation like maybe it's starting to fill up, right? It's a little geyser in little ducts opening and then emptying also through the sublingual, the smallest. These ones are mixed glands, meaning that they produce both mucus and a really watery part called a serous secretion. The parotids are just serous, a lot of watery secretion, and the submandibular is more serous than mucus. The sublingual is primarily mucus, and this is the gleeker. You ever been out to lunch with your friend, and then you tried to say something clever, and a tiny stream of saliva shot out of your mouth and onto her salad? Too bad. That's a gleek, and that's probably the sublingual gland. So it's an involuntary response to food stimulation. And sometimes when we talk or move our jaw, it compresses that gland, building up a little pressure so that the saliva shoots out. So it's not your fault. It's totally involuntary. You didn't mean to do it. Oh, also, we have lingual glands. So the tongue sort of begins to get a little moist when we think about food too. We also have lots of unicellular glands. that are all throughout the surface of the mouth. And so these just help to keep our mouth wet, not necessarily when we're eating, but just sort of that baseline level of moisture. And so if you have to go up on stage or you see or think about something stressful, your mouth may go suddenly dry, and that has to do with those other unicellular glands. These multicellular glands we see here are primarily involved in chewing, salivating, digesting. If we dive down into the cell, or the gland rather, we see the mucus-producing cells, and we see the enzyme-producing cells and the watery-producing cells. And so all of those different secretions mix together and then come out into the duct. The throat is the pharynx, and the pharynx, food flows through the pharynx into the esophagus. I'm sorry, I'm still sick. Excuse me. Clear my throat. Food travels through the pharynx into the esophagus, right? This is a swallowing tube, but the esophagus connects the throat to the stomach, and it is made of smooth muscle. We have some skeletal muscle in our throat that we have voluntary control over, and so to one degree or another, we can choose when we want to swallow. And when we do, the epiglottis flips down to cover the larynx, the voice box, and the food goes into the esophagus, first passing through the upper esophageal sphincter, and then through peristalsis, the food is squeezed down and down and down, and then the lower esophageal sphincter opens, and then it is squeezed through that opening and down into the stomach, a process that takes somewhere between 5 and 7 seconds. You can experience this if you drink something very hot or very cold, especially if it's your very first drink. So you haven't had anything to drink in, say, 10 minutes, and then you drink an extremely cold beverage. You can choose when to swallow it, which triggers the epiglottis to flip down, the upper esophageal sphincter opens, peristaltic waves squeeze the liquid down and down and down and down, and then 3 or 4 seconds after you swallow, you have this very cool splashing sensation here. And that's the opening of the lower esophageal sphincter and that cold beverage emptying into the stomach. So it's not a trap door. Food doesn't fall into your stomach, right? It's squeezed down into your stomach. And if you've ever choked on something or had the experience of feeling like something got lodged here, some of us have a very narrow lower esophageal sphincter, and so if I eat something very dry, like bread, without enough, sometimes I feel like it gets a little lodged here, and I have to drink to try to flush it down below. Some patients have very severe cases where it goes all the way down here and gets stuck, and then they have to bring it all the way back up, a condition called esophageal stenosis, which can be treated by an upper endoscopy using a balloon to sort of stretch out that sphincter. Okay, let's look at the stomach in a little bit more detail now. Once we swallow and get things down into the stomach, we see that the stomach is a very hollow and wrinkly organ. The wrinkles are called rugae, and they are there to allow the stomach to expand. So if I go to the China buffet, I want to get all my money's worth, people. I can put it down, and I love the General Tso's chicken, and so the egg rolls and all of that fluffy white rice really fills out my stomach, and so it can stretch out because these wrinkles will begin to flatten, and because the muscles can relax a bit, we can really wolf down our food and eat a lot in a short amount of time. I mean, if we have to. Somebody's got to do it. Okay, then what? Well, then this pyloric sphincter closes, and the stomach begins to produce large amounts of mucus to protect itself, and then it adds acid and enzymes to the mix, and these 3 layers of muscle tissue allow this thing to be like a big washing machine. The lower esophageal sphincter closes to keep acid from washing up into the esophagus. The pyloric sphincter closes to prevent acid from burning your small intestine. And then we put this puppy on wash mode. It's going to churn and squeeze back and forth, sloshing the acid and the water and all of the things you've eaten and had to drink until it's a nice, disgusting, soupy mixture. This mixture is called chyme, C-H-Y-M-E, chyme, but you know it as vomit. Sorry to be gross once again, but it is the nature of this chapter. If I am ill, the lower esophageal sphincter opens and the stomach begins to contract in a way, and the peristaltic waves begin to reverse their direction. It's called reverse peristalsis, at which point my salivary glands begin to kick in, releasing large amounts of mucus into my mouth. That's when you know you're going to be sick. You might feel sick, but you know you're about to be sick when the mouth starts to water. And then immediately before you actually throw up, you feel the contractions begin. And then seconds later, things come out the other end. Okay, so super gross, but the reason it tastes so nasty and sour usually is because you've just eaten something and the pH of your stomach contents is very low, super acidic. Take the copper off of a penny, acidic, and that's why it tastes nasty. Under normal circumstances, that acidic fluid is called chyme, and it will be introduced into the small intestine in tiny little bits, and thereby, or at that location, neutralized with chemicals so that the small intestine doesn't get burned. If we could do a tiny cross-section of the stomach, we would see it looks like Yellowstone, thousands of little geysers all over the place. And if we could dive down into the geysers, we'd see that they're very deep little pits and that there are all kinds of things, water and acid and enzymes gurgling up onto the surface. The mucus cells protect the stomach from digesting itself by laying down a thick layer of slime, sort of like a fish. You know, fish are actually coated in a thin layer of slime to protect them from microbes and to allow them to move more smoothly through the water. Well, in the same way, your stomach is covered in a layer of slime, and then the acid is poured out on top of that slime so that the food gets burned, but your stomach doesn't. Unless, of course, you have some sort of bacterial infection like Helicobacter pylori, in which case the goblet cells, the mucus-producing cells, get damaged, the layers of mucus become very thin, and then you start to develop an ulcer. A couple of very important cells we need to learn about within these little geysers. The little pits in the stomach are called gastric pits, and they produce mucus, hydrochloric acid, and an enzyme, or an inactive one, called pepsinogen. The mucus cells are goblet cells. The hydrochloric acid producing cells are parietal cells, and the ones that make the enzyme are called chief cells. All of these cells empty their secretions out onto the surface of the stomach to begin to break down food. But underneath them, there are endocrine cells that are going to help the stomach to communicate with the other parts of the GI tract, and for one stomach cell to stimulate another. These endocrine cells include the enterochromaffin cells, which make histamine, and the G cells, or gastrin-containing cells, and they release this excitatory hormone called gastrin. Gastrin is going to ramp up the other cells, more mucus, more acid, more enzymes. Just like any other feedback loop, there are inhibitory cells, in this case somatostatin cells, which after the stomach is done digesting the food help to turn things down so that your stomach isn't going to burn itself or digest or add acid to a lumen that doesn't have anything to digest, right? You don't want to try to release a lot of secretions on an empty stomach. Here's how acid is produced. We have no mechanism of storing up our hydrochloric acid between meals, and that's probably a good thing, because if you fell or took a punch to the gut, you could spill that acid into your intestines and you would die. So there's no acid bladder. We have to make the acid on demand. Do you remember which cell makes hydrochloric acid? The parietal cell. How does it do that? HCl, hydrochloric acid. The chloride from your salt, sodium chloride, is abundant in the bloodstream. And so we can just grab a chloride and actively transport it into the duct of the gastric gland. So there's half of our HCl. That's pretty easy. The hydrogen is a little more complicated. It actually starts with carbon dioxide, which in the presence of water becomes carbonic acid. Acids dissociate, remember, giving up a proton and creating a buffer, bicarbonate ion. Then, using ATP, we use a proton pump to pull the hydrogen from the inside of the cell to the outside of the cell. And there we've got our hydrochloric acid. Meanwhile, the byproduct, bicarbonate ion, is actually the most important buffer in the bloodstream. And your ability to maintain that very narrow pH, 7.35 to 7.45, is largely the result of bicarbonate ion. So whenever you make acid, you produce bicarbonate, what we call the alkaline tide, that helps to stabilize our bloodstream and keep it from becoming too acidic. The three phases of stomach secretion are the cephalic phase, the gastric phase, and the intestinal phase. The cephalic phase means the head phase, and it starts when we start to think about food. So if I'm at P.F. Chang's and I'm looking at the menu and I'm imagining how delicious that kung pao chicken is, or I see the waiter come by with somebody else's food, I am really thinking about food. My brain is getting visual stimulation and olfactory and auditory stimulation, and my stomach begins to turn on even before I've put food into my mouth. Histamine stimulates secretion of acid. Gastrin stimulates secretions of mucus, and pepsinogen, and hydrochloric acid. And so if I'm waiting too long for my food, I actually start to get a stomach ache. But under normal circumstances, the cephalic phase only lasts a few minutes, and then I'm putting food down. The presence of food within the stomach is what triggers the second phase, the gastric phase. This is primarily a neurologically oriented one as well. Medulla oblongata stimulates through parasympathetic signals the release of more histamine, more gastrin, more mucus, more acid. The stomach is in its element. It's going to work, producing a lot of secretions. Eventually, we have to begin to empty the stomach. And so these arrows do not represent the flow of food or food residue. This is showing us that the intestines are sending a signal to the stomach. Once food begins to flow out of this pyloric sphincter and into the first part of the small intestine, the duodenum, the small intestine says, okay, turn down the acid. Okay, we need a lot of mucus, but no more enzymes or acid. We're good. So we begin to downregulate decreased gastric secretions. Additionally, these two hormones, secretin and cholecystokinin, flow through the bloodstream to downregulate gastric secretions. Secretin says, okay, stop secreting. And cholecystokinin means the gallbladder mover. Chole means bile, cysto means bladder, and kinin, like the word kinesiology or kinetic, it means movement. The gallbladder mover hormone, so we already know where this one goes. It goes to the gallbladder to move it, to squeeze bile out. And CCK, cholecystokinin, also turns down the stomach. So this would be a great time to end the video. You should review the stages of gastric, what are they called? The phases of gastric function. Cephalic phase, gastric phase, and intestinal phase. You should be aware of neurological and chemical elements of each of these phases and to know when the phase starts and when it stops. Then you want to work your way backwards, looking at hydrochloric acid production, the different cells of the stomach and their secretions, and work forward. What are these secretions for? What are they going to do? How do they help us to digest our food? Good luck.